Hi, everyone. My name is Max Zinkus, and I will be presenting our paper, SoK, Cryptographic Confidentiality of Data on Mobile Devices. I worked on this with my co-authors, Tushar Jois, and my advisor, Dr. Matthew Green at Johns Hopkins University in Baltimore, Maryland. So that name is quite a mouthful. What I really want to talk about in this talk, in short, is defending mobile privacy. So we've all seen ads like these. This one's a classic, privacy, that's iPhone. But we've also seen articles such as these, access to, for example, iPhones in this case. And this sort of creates a clear contradiction. Somebody's got to be wrong here, right? So how do we go about exploring and resolving this conundrum? And I hope the answer jumping to everyone's mind is the same as ours, which is by analyzing the entire history of iOS and Android security features, bypasses to those security features, and forensic data extraction tools which have existed. So what do we mean by the entire history? We mean iOS and Android security guides, which do deep dives into the security features of these devices. We also mean the US Department of Homeland Security forensic tool evaluations. Effectively, these are analyses of which forensic tools exist, how they work, what they're able to extract from the major platforms, iOS and Android. These are executed per a NIST standard in a very sort of thorough way, as well as a few hundred other sources which span research papers, news articles, warrant documentation, blog posts, and many others, and hardware teardowns critically as well. So we looked at this history and what was sort of our product of all of this analysis. So we ended up writing about a 111-page report, which hopefully to everyone's relief, I will not be summarizing here. What did it contain from a high level? We have an analyzed history of security features in both iOS and Android. And in the SoK version of the paper, which we actually submitted to PETS, we look at the research papers which have led and followed this development, as well as their sort of impacts and implementations within the platforms. We looked at known bypass techniques to these security mechanisms, both in iOS and Android, sort of connecting themes between all of them, whether from a technical or other contextual perspective. And we looked at how these bypass techniques were realized into extraction tools. Here's an example of a set of tools which were analyzed by the DHS, and we digged into all of these reports to really break down what data was accessible when and how. We aggregated all of this information and provided some proposed improvements across the two platforms that we analyzed. And in the larger report, these really are from a technical perspective, maybe a development perspective. In the SoK version, we really look at research directions, which can go beyond the current state of the art and improve and address some of these issues. Now, there's an important aside I'd like to make, which is comparing illicit and lawful access to data, sort of both of which we consider unauthorized, but are obviously on very different sides of a legal analysis. Now, what I'm showing you here is a set of comparisons that we make between roughly equivalent methods of accessing data on devices, one lawful and the other illicit. And as you can see, these sort of connected techniques either rely on the same underlying technology or are otherwise somewhat indistinguishable to the end device. How is it going to determine whether to allow or disallow access to something, or how is a security feature supposed to be designed for one but not the other? And we dig into this disparity a little further in our paper. But in summary, we're sort of going to be considering unauthorized access from the perspective of what data can be extracted after the compromise of a device, and not necessarily so much whether it's a lawful access technique or an illicit access technique. So what were the summary of our findings? Something that might not be too surprising for this audience is that as we rely on the cloud more to store personal data, so too do we increase the propensity of leaks from that cloud data. Now, often data is stored in the cloud using provider-controlled encryption keys, not necessarily user-controlled. In fact, even in the case of, for example, iMessage, which is sort of famously end-to-end encrypted now, we see an example of Apple sort of subverting that end-to-end encryption if you also have iCloud backup enabled for iMessage, where they actually back up that end-to-end encryption key into your backup, which is encrypted by Apple, in case you need to, restore all of those iMessages, having broken all of your trusted devices, which was a bit surprising to us at the time. We also see the application of strong cryptography throughout these devices across iOS and Android. But we also unfortunately see, again, subversions or lack of coverage of this strong cryptography over user data, especially in tiered situations of access. For example, when a device is before first unlock, say it's powered off, that level of protection as compared to a device that is after first unlock, the first time it's been booted up and unlocked, even if it's at the time locked. Those two sets of data which are encrypted are very different. And realistically, how often do we carry our phones powered off and not first unlocked? And then finally, we see, in response to the secure hardware that's been deployed, we see advanced exploits. For example, I have a Graykeep device pictured here, which is known to extract data and be able to brute force passcodes on iOS devices, despite the secure hardware that was meant to prevent those attacks. So what were the key themes? We see, this history of extensive access to personal data, unfortunately, and this kind of cat and mouse way of security features and bypasses, which really leaves the end user in a situation where at any given time, they're not sure how much privacy they have. And we do actually also see law enforcement agencies using their seat at the table, using their access to, say, judiciary or legislative actors to push for increased access. I've pictured James Comey here from the famous sort of going dark testimony, wherein the FBI argue that they are having decreased access to data because of encryption, because of increasing encryption, which we know to not be the case. We know that the FBI now has more access to data than they ever have before. In some cases, too much that they haven't actually been able to thoroughly analyze all of it. And so, that's sort of the more bleak side of things. We do also see some positive signs. We see providers being proactive. When I say providers, Apple and Google. We see secure hardware being deployed in devices. We see increasing user-controlled encryption. And we also see this emerging paradigm of secure hardware actually being used in the cloud, which was one of the more key takeaways, which is that we have this industry-led trend of trusted hardware being deployed in the cloud, like hardware security modules such as the Titan HSM, those used in iCloud's Key Vault, or sort of the simulated HSM of Intel SGX, which is used in Signal's secure value recovery system, also sort of a backup service, a cloud backup service for the encrypted messenger. So we see this industry-led trend emerging, and providers sort of moderating their own access to user data. Now, this really clearly targets that malicious server, compromised server, or malicious insider, or even potentially subpoena threat models, closing out access and really enforcing user-controlled encryption in these cases. And then from a research perspective, we see emerging tools such as, say, Burnbox or other plausible deniable encryption schemes for mobile devices. And as well as an interesting project from Google, for example, we see the Trillion project trying to bring certificate transparency type transparency logs to the open source community. Some particularly interesting works in this space recently have also included how to protect cryptographic systems from compelled decryption. Scheffler et al. At Usenix, and then also how we can ensure that warrants are enforced in a correct way using cryptography rather than just sort of the discretion of an analyst at Eurocrypt last year as well. And I'm happy to share these links later. So we do see emerging research trying to address these challenges, although not in a complete way. And that's one of the things that we really wanted to have people take away from this, especially from a research perspective, was, as we develop cryptographic systems for mobile devices, let's really integrate the positive aspects of cloud and secure hardware services and offerings into those cryptographic systems, And then also let's take into account the cloud when we're developing these systems. You know, if we're storing a sensitive secret, is that going to be backed up to the cloud? What does it actually mean for our protocol for that to be disclosed down the line? From a developer perspective as well, let's continue to deploy these techniques. There's been some amazing work both across iOS and Android, and seeing that continue and putting these actual cryptographic tools in the hands of people is really vital work. And then to legislators, you know, we've seen the crypto wars come and go multiple times. You know, let's consider not rebooting it again. And from the advocates and researchers' perspective, let's continue to push back against these types of sweeping changes and sweeping limitations to user privacy. So thank you all so much for your time. I would love to field any questions that people have. And then this is a link to a website that we made to sort of summarize the results, especially of the larger report, which might be a bit unwieldy to read through and through. So you can scan the QR code if you like. There's also the URL it maps to. Thanks so much again. And yeah.